it also has quite a deep connection with algebraic number theory. And there's a second rough description you can give in this direction. And that is that the Chebotarev invariant of a finite Galois group is the number of random primes. When you choose primes at random, which will be done in a well-defined way later in the talk, and it's the expected number for you to generate your Galois group. Of course, this makes no sense, but hopefully later in the talk, I'll describe what it really, really means. Okay, so the plan today is I want to start off with some practical motivation of the way we study probabilistic generation, briefly, and a related invariant to the Chebotarev invariant. I'll then go on to define what invariable generating set means, and the Chebotarev invariant is rigorously, and then I'll tell you about this kind of curious motivation from Galois theory. I'll then go on and talk about a conjecture of Kowalski and Zivina from a few years ago and some of the results we currently know, and also some ideas from the proof. And if there's time at the end, I'll tell you a little bit about permutation groups. So all these sections are quite short. Okay, so practical motivation. So question is, why should we study probabilistic generation versus minimal generation? So probabilistic generation is concerned with finding some kind of small d such that there are loads of d tuples which generate your group. Okay, and minimal generation is just concerned with finding the minimal d such that there exists such a tuple. Okay, so why do we care? So I'm going to give you a kind of well trotted out example. It talks about generation of a5 to the 19. And a5 to the 19 famously can be generated by two elements, and the reason for 19 is that a5 to the 20 cannot be generated by two elements. The punchline usually when you throw out this example is that the EG is 2, which on first glance may be somewhat surprising. But the point here I want to make is that, okay, so there's a generating 2 tuple, but if you try to find elements at random, a generating 2 tuple at random, well, you'll be there until the end of time. Is this very, very small number, which can be computed due to a theorem of Cantor and Lubotsky from 1990. It's the paper where they proved the Dixon conjecture for classical groups. Okay. If you think about expected numbers of elements when you choose elements at random, so the waiting time is between 4 and 5 approximately. Okay. So perhaps this is a better way to think about generation for computational purposes at least. And as I said, I'll define this expected number of elements a bit more rigorously in the next couple of slides. Okay, and so there are a few different ways we can think about probabilistic generation. So one invariant that you might want to study is the invariant d epsilon of g. And d epsilon of g is the minimal integer k, such that k randomly chosen elements of your group will generate the group with failure probability at most epsilon. And Kolva and Derek and Igor Pak have some really nice results on this invariant. And it's quite an important invariant when it comes to computing composition trees in matrix groups and also in large base permutation groups as well. And in any talk about probabilistic generation, it would be remiss not to mention Dixon's incredible conjecture and proof by Dixon himself and Cantor, Lubotsky and Leibach-Shalev. So d epsilon of g is 2. So for each epsilon there exists an n such that if your finite simple group is big enough, then d epsilon of g is 2. Okay. So in this talk we want to study E of g, so the expected number of uniformly distributed random elements of g required to generate g. Okay. Now using Chebyshev's inequality from number theory, asymptotically studying d epsilon of g and E of g are similar. Give you, in certain situations, give you very similar results, at least that's so it's no loss to study one or the other, usually. Okay. So because this is quite important, I'm going to define it rigorously. So for a finite group G, I'm going to take a sequence of G-valued, independent, identically distributed, uniform random variables. Okay. Now we can define a random variable tau G by the minimum n such that the first n of these choices give us G. Okay, generate G. E of G is then the expectation of this random variable. Okay, so it's this E of T tau G. Okay. Now obviously D of G is less than or equal to E of G. It's a trivial lower bound. But an interesting question to ask is how big can the difference be? So the abelian case is the easiest case of finite groups, and Pomerantz computed E of G in this case. Now he actually computed it exactly in terms of the prime divisors of the finite abelian group in question, but I'm just going to put up the upper bound because it shows that it's bounded. So it's very, very close to D of G. So it's D of G plus some small constant. And because when you have a finite nilpotent group, generation is determined in the Frattini quotient, and in a finite nilpotent group, the Frattini quotient is abelian, and we also have this bound in the nilpotent case. Okay, so this is a corona. Now Cantor and Lubotsky in this paper that I mentioned earlier actually showed that the difference can be arbitrarily large. Okay, so we don't have this nice constant bound in general. However, the difference is relatively small depending on what you want. They told me Lucchini and Lubotsky independently proved that E of G is at most D of G plus a constant times log of the order of G. So for a finite group G, D of G is around, or is at most log of the order of G, so certainly E of G is logarithmic in G in the worst case. Okay. And this bound E of G is at most logarithmic in G is best possible if you just take elementary abelian 2. So it's best possible. Lucchini has actually proved an exact result for the expected number of generators. And this is quite a fun statement, I think. So if you can define a Mobius function on the subgroup lattice of a finite group. So you define mu G of G to be 1, and then mu G of H to be the minus the sum of the overgroups of H, mu G, which are K, and mu G of K. And then you have this strange formula for E of G. This is very useful, particularly for groups of small order. You can exactly compute E of G. And Andrea has done some interesting computations for small finite simple groups. So for example, I think other examples, E of symmetric group of 4, of course it can be generated by 2 elements, but it takes something like 3.2 elements to generate it if you choose randomly. Of course, most finite simple groups are just over 2 elements, will do. So now, what is invariable generation in the Chebotarev invariant? So the title of the talk. So a related invariant is as follows. And this was first defined by Dixon. So a subset x1 up to xd of a finite group G invariably generates G if upon replacing any element of my generating set by a G conjugate, then I still have a generating set. So so of course, my original set x1 up to xd will generate my group, but it's a much stronger notion of generation. Okay. So just some easy examples. S3, of course, if you take two cycles, then different 2 cycles will generate the group. Of course, they won't invariably generate because they're conjugate and the group is not cyclic. Okay. If you take a 2 cycle and a 3 cycle, of course, this will invariably generate. Another example, SNLP, if you take a set of transvections which generate your group, these are all P elements, so you can conjugate them to lie in a C of P subgroup. So of course they cannot invariably generate. And this is a bit more general, of course. If you have a fixed prime P, then unless your group is a P group, a P set can never invariably generate your group. And in fact, if G is an nilpotent group, if G is a finite group, then G is nilpotent if and only if every generating set is also an invariable generating set. So if your group is nilpotent, then this invariable generation is exactly the same as generation. So maybe not so interesting. That's quite good. The proof is quite straightforward. Okay, just a quick mention of infinite groups. Of course, all these definitions work in infinite groups as well. However, you have to be a bit careful here because sometimes the whole group doesn't invariably generate the group, which is a bit strange. So the easiest way to see this is if you take a general linear group over C. Every matrix is a Jordan normal form. You can conjugate to be an upper triangular matrix, so they all lie in the subgroup of upper triangular matrices, so they lie in a proper subgroup. Then the whole group will invariably generate the group. Now, of course, you can define a so-called, I think, Cantor, Lubotsky, and Chebotarev have done some work in this direction, and they define a so-called Jordan property. And if you say that the group has the Jordan property if the union of conjugates of a proper subgroup can never be equal to the group, then you can invariably generate. Then you can think about invariable generation in infinite groups. Okay. Okay, so now that we know what invariable generation is, of course, all these invariants that we define in generation can be carried over. So for example, you can say the I of G is the minimum number of elements required to invariably generate G, and this is the invariant in the title of the talk. So C of G is the expected number of uniform random elements required to invariably generate G. So I won't do this rigorously because it's the exact same definition as the last time, except you insert the word invariably before generate, and then it's done. Okay, and it'll become clear a little bit later why it has the name Chebotarev invariant. Okay, why do we care? I mean, it seems like a bit of a convoluted definition and just some arbitrary generalization of generation properties, but it does have a real motivation. And this brings me to the Galois theory stuff I was talking about at the start. And the questions on invariable generation actually go back to the 1930s. Van der Waerden had some great results in combinatorics and number theory, and he asked in the mid-30s, he asked, okay, if your group is the symmetric group and you choose permutations at random, how long will we have to wait before we have an invariable generating set? I don't think he used the word invariable generating set, but it was specific to the symmetric group. But nevertheless, this was the question. Sorry. Okay. This still doesn't tell us why we care, but I'm going to move on to that now. So, let me give you a Galois extension of the rationals. For each prime P, which is unramified in K, and I'll do an example in a second to remind you what unramified means. For each prime P, which is unramified in K, we have a well-defined Frobenius conjugacy class in the Galois group, and I'm going to call it Cp of K. So just an example, if you take K to be the splitting field of one acceptable polynomial, so polynomial with distinct roots over with the coefficients in Z, then the unramified primes are easy. They're just the primes which do not divide the discriminant. So the discriminant is the product of alpha I minus alpha j, where these are the roots. So this is quite easy. And also, these Frobenius conjugacy classes, at least representatives, are quite easy to come by in this case, because Frobenius's theorem tells us that Cp of k in this case, so P does not divide the discriminant of f, and Cp of k has cycle type n1, n2, up to nr, where these are the degrees of the irreducible factors of f modulo p. And you can do this for any prime, okay, as long as it doesn't divide the discriminant. Okay. So, just for technical reasons, if P is a ramified prime, we're just going to set Cp of k to be 1. And now comes the reason that the Chebotarev invariant gets its name. And this is Chebotarev's density theorem. It's a really deep theorem from algebraic number theory, which says that if we have a conjugacy class in our Galois group, fixed conjugacy class C, then the proportion of primes such that Cp of k equals C is the same as the proportion of elements in our Galois group. Okay, so if you've got a finite group G and say 10% of your elements are lying in a certain conjugacy class of order 7 or something, then there'll also be about 10% of primes, which gives Cp of k equal to this conjugacy class. Okay, so it's a really, really strong theorem. And in this definition, or this description of the Chebotarev invariant, I'm going to need this twice. So first of all, I need it because of this, we can certainly pick an n big enough so that there exists Cp1 of k up to Cpt of k for pi less than or equal to n, which give us an invariable generating set for G. Now I'm cheating a little bit here because I'm saying that a set of conjugacy classes generates our group. Invariable generation was defined to mean elements generate the group, but it's the same thing because they're the same with the conjugacy. Okay? Okay, so we can certainly choose such an n. So then if we choose, so if we have a fixed big N, and if we choose a random prime pi less than or equal to n, then we again get a sequence of independent, identically distributed random variables with values in the set of conjugacy classes of G. So these are the Cpi. Okay. Now we define a random variable which depends on n. So we're going to call it tau ig of n. So it's the minimum n such that the first n of my primes gives me an invariable generating set. And then using Chebotarev's density theorem, we can prove that the limit of these expected values is actually this C of G that we started with invariable generation. So this is why I said at the start that's the number of random primes you need to generate a Galois. This is where the story comes from. Okay. So this is the second place that we needed Chebotarev's density theorem, more deep place. Okay. Okay. I just want to run through a couple of kind of interesting asides as to maybe more specific motivation. So Van der Veerden asked about the case Sn. This is probably well known, but this is kind of I think I made a meal of stating this. But if you take if you imagine that you're choosing polynomials of degree n, or integer polynomials of degree n, and you imagine them to be in a box. So in other words, the coefficients are at most some fixed b, okay, some fixed integer b. Then if you choose a polynomial at random, then with probability tending to 1, as this b tends to infinity, your polynomial will both be irreducible and have Galois group, the full symmetric group Sn. Okay, this is why this is Van der Veerden's theorem actually, and it's in the same paper he asked this question about if you choose randomly elements of the symmetric group, how long do you have to wait to prove that it's equal to that the Galois group is equal to Sn. Okay. So in some sense, in this way, most polynomials of degree n over z have Galois group, the full symmetric group Sn. Okay, just an aside too, and I don't know much about this, but the case where you have the general linear group of degree 2 over a prime field is also quite interesting to number theorists, because if you have an elliptic curve and you take the torsion, so this elliptic curve is an abelian group, and you can take the torsion points of this elliptic curve, the elements of finite order, and if you fix a prime p and attach the torsion points, then the Galois map, the Galois representation of this elliptic curve embeds into GL2 FP. And there's a famous conjecture called Serre's uniformity conjecture, which says that this is surjective. Okay? Sorry, if the prime is large enough, it's surjective. And Serre has proved and with certain extra conditions on the endomorphism ring of the elliptic curve in question. And I think Serre originally claimed that there was a constant lower bound for the primes, but I think now it's universally conjectured that the prime is 37. So any prime bigger than 37, you should get the full GL2 FP. Serre has proved that there exists a lower bound for p, which depends on the elliptic curve in question. This is quite a big conjecture in algebraic number theory. Okay, so last aside, there's a kind of algorithm underlying this discussion. So the algorithm is as follows. It's kind of an algorithm because it's not really because you need a guess at the start. But okay, if you can find a group X, so the point here is that you want to compute the Galois group of a fixed number field K over Q. Okay. And say that you know that your Galois group is contained in a group X. So maybe it's the Galois group of a polynomial of degree n, and then you can say, okay, my group is in Sn. Or if you're in the situation of the last slide, and K is generated by the torsion points of the elliptic curve, then you know that you're in GL2FP. Okay, so symmetry considerations gives you a guess at the start. And say you want to prove that your Galois group is equal to X. What can you do? Well, you can choose random primes, and you can say if you're in the polynomial situation, reduce modulo p, this polynomial, and compute the Frobenius conjugacy classes, and then this gives you an element of your Galois group, or a representative for a conjugacy class in your Galois group, and you keep going until hopefully you can generate X. Okay, and the Chebotarev invariant, I mean, there's a certain kind of Las Vegas algorithm going on here, because, for example, if you're an Sn, so the first step is, okay, you try to prove that your Galois group is equal to Sn, okay? And the Chebotarev invariant measures the efficiency of this. So it measures the expected, if it is equal to Sn, it gives you the expected number you should need to generate. So if you choose this number and you don't get Sn, then maybe you move to the maximum subgroups and then you try again. So this is quite a useful invariant in this as well. And there's much better algorithms, but this has been useful for more theoretical purposes actually, because A few years ago, the Jew of Kowalski and Savina found the first example of number field with a Galois group, the file group of E8. So I think it was 240 dimensional polynomial, they wrote, or degree polynomial, they wrote it down, and they proved much more strong results as well. In some sense, they found a matrix group, a representation of E8, such that a random matrix in here, well, if you take a random matrix and choose Galois, take the characteristic polynomial, and the Galois group of this polynomial will actually be equal to the void group. And there are more applications in this direction as well to algorithms to find out if an arithmetic subgroup of GL and Z of SL and Z is Zariski dense. Okay, so what do we know about this and some conjectures? Well, as I said before, we have D of G is at most E of G, okay, obviously. But of course also E of G is at most C of G, because invariable generation is a stronger notion than generation. This is just reminding you what these letters mean. Again, we ask how large can the difference be, okay? Just for context, there are some really interesting examples of groups such that invariable generation and generation are in some sense the same. So I mentioned earlier in the talk that if you have a finitely important group, then certainly we have D of G is equal to Di of G. But perhaps more interestingly, if you have a finite simple group, then Di of G is 2 as well. And this is proved independently by Cantor, Chebotarev, and Gareth Tracey as well. Okay. Almost simple groups, there's still some work to be done, I think. Okay, G is abelian, of course, E of G is equal to C of G. Okay. No conjugation in these groups. And as I said before, if it's nilpotent, then we also have E of G is C of G. So Pomerantz's result holds if we replace E of G by C of G as well. Okay. So again, we ask, can we bound the difference in some way? The answer is no. So I'll just remind you about the Tommy and Lubotsky's result from 2003. And they proved that E of G, the difference between them is at most constant times log of the order. But Kowalski and Savina proved in 2010 that really, I mean, if you think about the easiest non-important group, you might think of an affine group, FQ semi-direct FQ cross. But the Chebotarev invariant is crazy here. It's around Q as Q tends to infinity, which is around the square root of the order of the group. That's huge. Okay. So if you pick elements of an affine group at random, it'll take you quite a long time to find an invariable generating set. Okay. So we'll go on to so even in the meta-abelian case, it's very, very different. Okay. And this also tells us, of course, that we can't hope to have some kind of reduction lemma where we bound C of G in terms of maybe C of G mod n and C of n or something, because the abelian cases are easy, but meta-abelian is crazy. Okay, so there's the proposition again, and they had quite an interesting paper actually in 2010 where they computed lots of small examples. Even C of G for the finite simple groups can be quite large for the small ones. Overall, the examples they computed, they found that the worst case with a constant and everything is 5 over 3 times the square root of the order. So asymptotically, this is the best case, of course, by the proposition above. But it's also the worst case in general when you look overall small finite groups. Easy example, it's C2 cross C2. Now so this is easy to prove. So if you want to try and generate C2 cross C2, well, if you choose a random k tuple G1 up to Gk, the only way you're not going to generate it is if all of your Gi's are in a cyclic subgroup. And therefore, it's quite easy to calculate the failure probability. So it's 3 times 2 to the k minus 2 over 4 to the k, taking away the intersections. So then you can find C of G just by the usual summing up of expected value, or of probabilities to get expected values, and you find it's 10 over 3, which is 5 over 3 times the square root of the order. Okay, so a really easy example gives what they thought was the worst case. Okay, I just want to talk about now some possible approaches to proving this conjecture. So for a positive integer k, I'm going to write PIGK for the probability that k randomly chosen elements of Witten chosen uniformly with replacement, etc., invariably generate G. Okay? Then C of G, just by the usual definition of expected values, is this guy. Okay, so the sum of the fitted probabilities. Okay. I'm going to do quite an obvious thing. So, if you want to find out if a subset of your group generates your group, you just have to check it's not contained in any maximal subgroup. Okay, and a similar notion holds here. So, for a subgroup H of G, I'm going to write H tilde for the union of the conjugates of H. Okay, now a subset x1 up to xk, as I said, fails to generate my group if it's contained in some maximal subgroup. Okay. Fails to invariably generate if it's contained in some union of conjugates of maximal subgroups. Very similar notion. So we have this this upper bound for these failure probabilities. It's at most the sum over the representatives of the maximal subgroups of this the size of this m tilde over the size of g tilde k. Okay. Okay. So I'm just going to now give you some results that we know. So using this approach, Cantu, Vygotsky, and Shalev in 2011 proved that C of G is around a constant times the log of the order of G times the square root of G. I should have wrote those the other way around. It's not log G root G, it's square root G times the log of G. Okay. And then Andrea proved the asymptotic version of the conjecture of Kowalski. C of G is around big O of the square root of the order of G, a similar approach. Okay. And then a couple of years ago, Andrea and I proved the following. So, if G is a finite group, and for each epsilon bigger than 0, we can find a constant C epsilon, such that C of G is at most 1 plus epsilon times the square root of the order of G plus C epsilon. And if G is solvable, then the conjecture of Kowalski and Zavina holds. So in some sense, number 1 is asymptotically best possible because of this result of Kowalski and Zavina, where for the affine groups, the affine groups are the worst cases. But we don't have numbers in the general case, just in the solvable case. So the idea of the proof is as follows. So we're going to look at, the idea that I gave you before is that we look at unions of equivalence classes of maximals, maximal subgroups, and these equivalence classes are conjugacy, okay? Conjugacy classes. But the idea here is to look at kind of coarser equivalence classes, okay? And I'll tell you what I mean now. So if we take a chief factor V of our group, okay? So V is either an elementary abelian group or it's a direct product of non-abelian finite simple groups, isomorphic non-abelian finite simple groups. Now if I take a maximal subgroup of my group and take G modulo the core, it's a primitive permutation group. So therefore it has either a unique minimal normal subgroup or there's some cases where it can have two. In any case, we say that G modulo the core of G of M is of type V, okay, if it has a minimal normal subgroup which is G equivalent to V. Now, G equivalent is essentially G isomorphic. So, if our group is an elementary abelian group, so if G modulo the core of M gives an affine primitive permutation group, then it just means that the socle of G modulo the core in G of M is G isomorphic to V as modulus. So that's all it means. It's similar in when you have a direct product of finite simple groups, but I won't write it up, but it's very similar, so you can just think of it as G isomorphic. Okay, so apologies for more terminology, but we see that the subset x1 up to xk satisfies the V property in G if it's contained in M tilde for a maximal subgroup M of G of type V. So then the subset x1 up to xk fails to invariably generate G if and only if it satisfies the V property for some G factor V. So now we have a new probability. So I'm going to define PG V of K to be the probability that a randomly chosen K tuple of elements satisfies the V property in G. Okay? It's contained in one of these union of conjugates of a maximal subgroup, which has this property that G modulo the core has a minimal normal subgroup, which is equivalent to V. So first proposition is as follows. So if G is a finite group, we take representatives for the non-central G factors of G. Now, by non-central G factors, we mean those which are not contained in G modulo the derived subgroup of G. So the ones with some non-trivial action on them by the group. Okay. So basically, the contribution of these non-abelian G factors is the first term, so it's the sum over V in these non-central G factors from k equals 0 to infinity of PG V k. And the contribution of the central G factors is the number of generators of the abelianization plus this small sigma from Pomerantz's result. So it essentially comes from Pomerantz's result. Okay. And then we have a reduction lemma. So I said to you before that it's difficult because of this result of Kowalski and Zavina. We can't really hope to have any nice reduction. C of G is that whole C of G mod n plus C of n, and then we can just reduce to simple groups. But what we do have is as follows. So we can prove that there exists some G factor V and a normal subgroup n of G, such that C of G is at most C of G modulo n plus a sum of these probabilities that the randomly chosen k tuple has property V. So we can reduce the counting these probabilities or computing these probabilities in one fixed V. Okay? And our idea is going to be that we can bound the C of G modulo n with induction, and then these PG of k's we'll have to work on. Okay. Okay. So I'm just reminding you about the reduction lemma, and this is just what I said. If we use induction, we can compute CG of G mod n. So we have to. So our task now is to compute these PG V of k's. Okay, for a fixed G factor V of G. And okay, the point here and why this is quite useful is we can show that this computation can be done inside so-called V crown of G. So it can be done inside inside of a finite group which is a very particular shape. And this makes our computations much more useful. So what is the V crown? Well, I'm going to take all my maximal subgroups with this V property. So G modulo the core of M has a minimal normal subgroup which is G equivalent to my V. Okay? Or G is a normal subgroup. Sorry, I take the intersection of all these guys. I take RG of V. And this is a normal subgroup of G. And if I take the quotient, it's called the V crown based power. And these crowns are very useful for results on generation, because they can also be, they also completely determine generation properties of G. Okay, so if I want to compute D of G, then D of G is actually equal to D of G modulo RG of V for some crown. Okay, so in some sense, the question of generation can be completely reduced to crowns. Variable generation can't necessarily be, but it gives us enough to do what we want to do here. So if V is abelian, so I said that these groups have a very particular shape. If V is abelian, it's particularly nice. So if I look at my maximal subgroups which have the V property for a fixed V, if there are a delta of them, okay, then my G modulo or G of V has shape V to the delta semi-direct H, where H is the induced linear group on V. So H is just G modulo CG. Okay, and this extension splits and it's really nice. And the action of H on V to the delta is diagonal, so it just acts on each copy of V individually. Okay? Okay, if V is not abelian, it's very, very similar. The only difference here is the H on the top doesn't give a split extension. Okay, so H is again G modulo the centralizer in G of V, but it's not split. And H is the induced group of automorphisms, etc. Okay, so back to this reduction lemma again. So we can do this inside this V crown. Okay, not trivial, but we can do it inside the V crown, and it's essentially the reason that I gave before. Generation properties usually reduce to generation properties inside the crown. Okay, and this means that we may assume, just to compute these probabilities, that G has this shape V to the delta dot H, where H is equal to G modulo CG. Okay, so I first want to think about the case where G is abelian, or sorry, V is abelian. Okay, so V is an elementary abelian group, elementary abelian P group. And we prove the following. This is non-obvious, but I'll give you an idea. So C of G is at most a CG of C of G modulo n, and this computation here is just a bound on this PG V case. Okay. So I'll tell you what this notation means. So the delta is the number of is the number in the top there. Now we look at the first cohomology group of H acting on V, because this is a finite group and V is irreducible, and H of V is a field, so we can look at the dimension over this field of the first cohomology group. Then we add a constant, Q over Q minus 1, and then we multiply by H modulo H star. Now H star is a strange thing, but it turns out to be really important in our calculations. H star is the number of elements in H such that H fixes some non-zero vector in V. Okay. So for example, if the characteristic of V is P, or the underlying field is P, then every element of a CLOP subgroup will be in here because they all fix something. And then this theta is just 0 or 1, depending on whether I have a small delta or not. Okay. So the point here is that we've now reduced, so this delta dot theta is small and this q mod q minus 1 is small. So we've essentially reduced the computing H mod H star and the dimension of this cohomology group. Okay. The second one is useful in particular circumstances, but the top bound is the one that we really need to work on. So, what about the cohomology? Well, H is soluble, it's easy, it's 0. Okay, if you have a finite soluble group acting faithfully and irreducibly on the module V, then the cohomology is 0. And in general, there's been a lot of work to show what we can say about the group if H1 of HV is non-trivial. In particular, it has a unique minimal normal subgroup and it's non-abelian, and there's other results on when you reduce the module to this minimal normal subgroup, the composition factors of the module, etc. Okay? And this lemma is useful. So we've shown that there exists an absolute constant C such that this H star is big if, this M is supposed to be the dimension of H1 of HV, sorry, I forgot to say that. Okay, so the point is that if H1 of HV is non-trivial, then H star is big in relation to the dimension. So if we just go back, then, okay, so either we have this is 0 or this thing is small. That's the idea. Okay. And this gives the result in the case where V is abelian. With some extra work. I'll just tell you briefly about the case when V is non-abelian. So we have, in this case, we have V is isomorphic to direct product of T copies of a fixed finite symbol group S. Okay. Then for large enough G, we actually have the sum. The sum of these probabilities of P, G, V, and K is around log squared the order of G. This is highly non-trivial. It actually comes from the proof of Fulman and Granick of the Boston-Chalav conjecture. This is where we get it. Now we can do something weaker to give us a weaker bound in this, which is enough for our purposes as well. So we don't need the full power of Fulman-Granick's proof, and also lose our Peeber. I should say, given that Peeber's a member of us. Okay. So this conjecture states this Boston-Chalav conjecture is just that the proportion of elements in a finite simple primitive group, the fixed point free elements is bounded away from 0. Okay. And the relation here is that, okay, if you take a primitive permutation group, the union of conjugates of point stabilizer is M tilde over G is the proportion of elements which fix a point. So this is the relationship. This is where we get it. Okay. I'll just tell you briefly about a partial converse. So maybe a natural question to ask is, okay, if I have a large Chebotarev invariant, because we don't have many examples of groups with a large Chebotarev invariant, so maybe we look for more. So does it in some sense look like this affine group? So we proved the following. So this is a bit of a mouthful, but the point is that if we do have a large Chebotarev invariant in the sense that there exists an epsilon such that C of G is bigger than epsilon times the square root of G, then we can find a lot of constants, a few constants such that G has a large quotient which is dominated by an affine group. So this is kind of the idea. So H is a linear group here, so the root product is the action on V. And number 2 tells us that it's a large quotient, and also the size of H and V are comparable here. So this just shows that, okay, if you do have a large Chebotarev invariant, then you do have a big affine group lying around somewhere. So, just going to finish with this. Back to van der Waerden's original question. So of course he didn't ask it in this language, but you can interpret it maybe as asking what is the Chebotarev invariant of Sn, because we still haven't answered that. This is really, really lovely. Results by Eberhard, Ford and Green, and Pimentel, Paris and Revin. So if G is the symmetric group or the alternating group, then in contrast to Dixon's conjecture, if you choose 3 random elements, you won't invariably generate your group. It tends to 0 as n tends to infinity. Okay? This was proved by Pimentel, Paris and Revin. But what Eberhard, Ford and Green proved was that if you choose 4, then the probability is bounded away from 0. Okay? Really interesting results. Essentially, they're results in number theory, because you look at intersections of some sets of integers, and these follow a Poisson distribution, and then they use some really nice probability and combinatorics to prove these results. So then C of G is at most 4, we can show. Sorry, is at least 4, we can show. Now it would also be interesting to see what happens for other almost simple groups. Okay. I should say that Eileen McKemmy, who's a student of Bob Goralnik's, has recently put a paper on the archive that I need to look at. It's very interesting for other finite simple group, for the groups of any type. Let's try and prove something similar. Okay. So, given, I think this is the last slide. So, given the motivation from Galois theory, it's natural to ask what happens for permutation groups in general, not just Sn. Okay. So what can we say about C of G in terms of n, where G is just a subgroup of Sn, not necessarily the whole group? Well, from Andrea and I's results, we can only say that C of G is around square root of n factorial, which is not very nice. Or if it's soluble, then you can show that soluble permutation group is at most 24 to the n minus 1 over 3, and then you take the square root. But still, these are not very nice. And this might be reasonable to ask, is it linear in n, or maybe polynomial in n? And I think from the examples we computed, we think that it's linear in n. What we can prove is that if it's either solvable or primitive, then it's polynomial in n. We can't prove linear. It seems tricky, but if you find some ideas, then that would be great. And we can now extend this in the following way. So if we take R to be the maximum of the ranks of the finite groups of Lie type occurring as subsections of G, then D of G is at most n to the C of R. Okay, so the constant depends on these ranks. Okay, so we kind of reduce things to proving it actually depends on this H mod H star that I told you about before, the proportion of elements of a linear group which fix an element, in particular when H is a finite simple group. And I think this is all I have. So thank you.
A stupid one, but in your reduction theorem, I got confused about what the normal subgroup n was.
Yes, so the normal subgroup.
It can't be the identity, right? Well, that's vacuous.
No, so it actually comes from. It's actually one of these RGUVs that we have before. Well, it's not actually. It's so there's a result of S squared which says that it's kind of like a Frattini type result, which says that if you have a finite group G, then there exists. So let's assume the Frattini subgroup is trivial, but it holds. If you have a finite group G, and then there exists a chief factor which occurs as a normal subgroup, not just a chief factor, such that the RG of V can be written as a direct product of this chief factor and something else, and then the something else is a normal subgroup, and this is the n.
Right, so when you said there exists an n, your more detailed version actually tells you exactly what the n is.
Yeah, exactly. Tells exactly.
Did you say what C or Sn is? You just said
no,
it's at least 4.
It's at least 4. That's all we know. Yeah. So Eberhard, Ford, and Green's results allows us to say it's at least 4, but we don't even know if the limit exists. Maybe it depends on the prime factorization of n. But it would be really interesting to see what it is precisely.
Is it definitely bounded by something?
Yeah, not sure either.
Mm-hmm.
Yeah.
But then the other simple groups you said, highly tell me the
Yes,
result? What
yes.
are they?
I'm not actually sure yet because I haven't seen it, but I think she has some results for the groups of lethal effect.
So it's at least something.
I think she proves a similar result to the statement of Eberhard, Ford, and Green and Mansell, Paris, and Ravin, where she looks at the probability rather than the actual expected number. So she proves that.
It's a very similar kind of result.
It's a
I have
similar-
seen it, but I can't
yeah.
remember what the numbers are. But yeah, it's constant numbers depending
Yeah.
on exactly what Lie type group
Yes.
it is. And she doesn't do all the Lie type groups. She does the classicals.
Yeah, I think it's just the classicals and the exceptionals are still open. Yeah.
Because she's pulling back the SM stuff to act like the Weil group.
Yes, yes, exactly. Yeah.
Any more questions? Yep.
Your result about G is either soluble or primitive.
Yeah.
It's, C of G is a polynomial in N.
Mhm.
That seems a little strange because there are lots of different subgroups contained in Sn.
Sure. So
Is that a bound you're speaking about?
yes. So the reason that we prove that this is true is that well, the chief factors, we reduce to studying the chief factors, and if you have a permutation group, then G is a subdirect product of its transitive constituents, and then chief factors will only come from these transitive constituents. So we reduce to looking at transitive solvable groups, and these have order exponential in n, and so they're easier to study, and we don't have. And then when we reduce to looking at these irreducible linear groups acting on the chief factors, then we can use kind of Supernenko theory to look at Reed's products, and we study them in this way. And this is why, and also irreducible linear groups, irreducible solvable linear groups are quite small, so it makes it easier to think about. And primitive permutation groups, which are not SN array and also small. So we know a bit more about this as well.
You just mean there's an absolute constant such that C of G is less than n to C?
N to C, yes. We think C should be 1, but, or at least modulo some multiplying by constant the front. We can't find any example where it's not linear.
Okay, thanks very much.